Hello, ladies and gentlemen. It is time for your daily dose of Dorfler. All right, so now we are getting ready to take on a new adventure, one of the last adventures we're probably going to have for this semester. Possibly. It all depends on how everything works out, okay? In this chapter, we're going to be looking at work, power, anything that kind of goes along with those concepts, okay? So we are actually going to start off with our discussion on work, okay? So you have to ask yourself, what does work mean to you, okay? Right now I'm working because I'm performing my job, but they're just like energy, which we'll also talk about energy in this chapter. It is a term that can mean quite a few different things depending on who you ask. So what we're going to do in terms of our definition is we're going to apply it scientifically. So we have to put some set parameters on how we can actually define work. So in this first section, we're going to recognize the difference between the scientific and ordinary definitions of work. Define work by relating it to force and displacement. Identify where work is being performed in a variety of situations. And then calculate the net work done when many forces are applied to an object. Okay. So you also, for this, you're going to want your calculator. You're going to want your formula sheet because you're going to add a couple of formulas today. Really, it's going to be the same formula, just in a couple different ways, because there are things that you can input into this formula, just substitute it in. So you want to have that handy. Along with this video, I will also be providing copies of the notes and the test review. So you can follow along, print those out if you need to. If you need me to print them, send me a note at the earliest convenience. I will get those as soon as I can and place them down by the office for you to pick up. No need to come up here and get them. Just hop in the front doors, pick them up. You can be on your merry way. Let's begin. So the definition of work. Scientifically speaking, it is when work is done on an object when a force causes a displacement of an object. That is huge. And what I mean by that is it has to cause a displacement. You can sit here, I can attempt to push my desk where my computer is as hard as I can. And I feel like I'm doing work, right? I'm getting sweaty, I'm putting in a lot of effort. But if this desk does not budge because it is anchored to the floor, I'm not, scientifically speaking, doing any work. So I have to cause a displacement. Even the smallest bit of displacement constitutes work being done. And work is done when the components, and only when the components of a force are parallel to the displacement. Okay, so that's important as well. It has to be in parallel with the displacement. So some signs of work is going to be important. Okay, we've been talking about vectors and signage and all that good stuff here. And so we got to talk about when work is going to be positive and when work is going to be negative. So when work is going to be positive, the component of force is in the same direction as the displacement, like what we just saw in the last thing. Okay, when we lift a box upward, okay, work done by the force is me, I'm the force, is positive because the force is upward and the box is moving in the same direction. So the box's displacement is also upward in the same direction as the force. Then we assign a positive signage. It will be negative when the force is in the direction completely opposite of the displacement. Friction, okay? Kinetic friction. When we have a sliding box in the floor, when that has kinetic friction. So the box is going to slide in one direction on the floor while the kinetic friction is acting 180 degrees opposite to that. So that's when it becomes negative. And just so you know, the cosine of theta will be negative for angles greater than negative, but less than 270. So typically when we talk about this, the force is going to be, I'll show you. So here's your new equations. So we have work is equal to force times distance times the cosine of theta. Now, the units for work will be joules, Joules. Capital J is the label, essentially. And really, it's 1 joule is equal to 1 Newton meter, Newton times meter. You can see that from the formula, okay? We can also have variations of this equation where we can have work is equal to the kinetic friction times the displacement times cosine of theta. And that will be typically when we're talking about frictional forces and calculating those. But you can also break down the kinetic friction by this way. Fk can equal to the gravitational force multiplied by the coefficient of kinetic friction, mu k, multiplied by our displacement times cosine of theta. So you want to write down all 3 of these things. Again, this one kind of is a standalone here when we're talking about work done on an object. And this one is typically assigned to the opposing forces, okay? So let's look at a couple of examples here. Let me get situated here. Okay, so sample exercise A says, how much work is done on a vacuum cleaner pulled 3.0 meters by a force of 50 newtons at an angle of 30 degrees above the horizontal? Okay, so take an image of what we were given here, and let's jot that down. Okay, zoop. Okay, let me dim this just a smidge. Okay. So we know that the force was 50.0 newtons. We know the theta, the angle at which the vacuum cleaner is being pulled, was 30 degrees above the horizontal. And the displacement was 3.0 meters. We need to calculate our work, capital W. Okay? So, since we're assuming that we're having a constant force, because this is when really the equation works, is when we're talking about a constant force. So we have work is equal to F times D times cosine of theta. Plugging in our values here. Our force was 50 newtons. Our displacement was 3 newtons. 3 meters. And our cosine was, or theta was 30 degrees. Plug that into your calculator, and you get that 130 joules of work was done on that vacuum cleaner. Pretty simple, pretty straightforward. Now let's go to another example to where it's going to be multi-step, okay? Excuse me. Going back here. Practice 2. A worker pushes a 1.50 times 10 to the third Newton crate with a horizontal force of 345 newtons at a distance of 24.0 meters. Assume the coefficient of kinetic friction between the crate and the floor is 0.220. Okay, so we have an A, B, and a C here. So let's write down what we know, okay? We know that, excuse me, our displacement, let me get out of here. We know that, again, I'm just kind of jotting this stuff down for future reference here. We know that the displacement is 24 meters. We know that our coefficient of kinetic friction, our mu k, is 0.220. And our theta is actually going to be 0 degrees because it says it's along the floor or across the floor. So it's going to be 0. We know that we have a force applied of 345 newtons. And we also know the gravitational force, believe it or not, of the box itself. It's told us right there in the first line, 1.50 times 10 to the third newtons. Okay? Again, we get that because it is the mass of the box times the acceleration due to gravity. That is its gravitational force. Okay? Excuse me. So let's solve this first. So we need to figure out, A, how much work is done by the worker on the crate. Okay? So we know, we're going to call this W1 because we're going to be solving for work twice. So this is F applied times displacement times cosine of theta. So we get 345 newtons times 24 meters times cosine of 0 degrees. And for part A, we find that we have 8.28 times 10 to the third joules of work done by the worker on the crate. Part B wants us to determine how much work is done by the floor on the crate. Okay, so this is now going to go into those other formulas that we saw a few slides back. So call this W2 because we're talking about the floor on the crate. So this one's going to be Fk times displacement times cosine of theta. Okay, but remember that this is going to be working in opposite direction of the actual force because this is a frictional situation. Okay, so it gets a negative sign. And this equals Fg times mu k times d times cosine of theta. Now, if you ask yourself where this Fg times mu k comes from, well, it comes from the previous chapter, chapter 4, when we were looking at how we calculated the coefficients. Okay, so that's where that comes from. Anyway, we can now go ahead and plug in our numbers. So again, the Fg was 1.50 times 10 to the third newtons. Coefficient of kinetic friction was 0.220. And we had a displacement of 24 meters and a cosine of 0 degrees. Okay, so multiply all that through, we get negative 7.92 times 10 to the third joules. And last but not least, I'm going to move this down here. For part C, we have to figure out what is the net work done on the crate. So our net work, W net, is equal to W1 plus W2, or 8.28 times 10 to the third joules, minus 7.92 times 10 to the third joules. And so we get a net work of 3.6 times 10 to the second joules. Okay? So that is how we utilize the work equation as well as the kinetic friction and coefficient of kinetic friction to help determine what net work is done on an object. Okay? So again, watch this video over if you want to. You can do a couple practice problems. I'm going to practice A. Can't remember what page it was on, sorry. But it's chapter 5, section 1. You will be getting the problem bank with this most likely tomorrow. It'll be the only thing you have to do tomorrow. And with that being said, if you have any questions on this, just hit me up. I will respond to you as soon as I can. But until then, everyone, have a wonderful day. Bye-bye.